All right, and now we started recording. It is 7:10. Yeah, let me just turn my camera on, actually.
While she's doing that. So thanks guys for coming to the the last main lecture. There's another one, very important lecture next week, but it's Jessica performing her not performing, but talking about her research.
Yeah.
This is all in the air stuff, but she actually did research in last summer. And her professor, which is a professor at University of Alberta, if you don't know, is one of the best reinforcement learning institutions in the world, probably.
Yeah.
He'll be coming to give a talk on something.
Online, not coming,
Online,
but
yeah. But so the reason U of A is really good is because the founders of RL, you can almost say, it's like the Jeffrey Hinton of RL. Richard Sutton is there, and he's a prof there. So yeah. So please, this is a very important lecture, but next week is also important.
Yeah.
And yeah, we really appreciate you coming here, and I promise this will be a good one. As always, we always start with some AI news. So this is from recently, AI Learned Minecraft, meaning they can generate Minecraft, right? There's a link, you can play it out for free. Yeah, I mean, it's cool, right? It's back then, I mean, just Google, I think NVIDIA or somebody, they're like they're trying to make Doom, like the really old Doom games in AI, but some random AI company just came out with Minecraft, so I think they have them beat. Yeah, and
okay, actually, a follow-up on that. I actually searched up the company. If you guys are curious, it's called. I don't know if it's
that's the
AI.
name of the AI, but the company is something else.
AI, yeah.
Something else. I don't know, whatever. But yeah, so that's really good. That's really cool. If you wonder what it is, it's a transformer because you realize after doing AI a lot that you can have all these fancy algorithms and everything, but nothing really beats feeding 1 billion data points to a large language model. So it's usually how it goes. Brief recap. This was last week. These are the Bellman equations. It's basically just an idea of expressing one quantity in terms of another one. So, for example, the value, I hope you guys are familiar with what the value is right now. The value of the current state is simply the reward you get plus the value of the next state. I think that makes sense, right? Like where you are right now is the value of where you are right now is the reward you get. You go somewhere else, it's the value of wherever you end up with. It's sort of an estimation of the reward you have right now. Well, in this case, it's not an estimation because it's everything, but later on you'll see. The state action value function, the Q function, and this will be a big player, a main character in our lecture today. The Q function is very important. If you don't know what it is, please ask. It's basically the value function. It's the value or how good a state is, but also it assumes you've already picked an action. So it's how good you are in this state and how good an action is in this state. So you can see the input is not just S, it's S comma A. It's the action, right? It includes the action in the value. So how good this state action pair is, if you will. So it's also very simple. I mean, not very simple, but the idea is simple in the sense that how good this state action pair is the reward you get after taking that action, plus how good the next state action pair is. Once again, it's this idea of expressing one quantity in terms of the next one. Then this is the Bellman optimality equations where we are dealing with optimal value functions or the best you can get in a particular environment. And once again, it's the same idea, right? The best value at this state is the reward you get plus the best value at whatever next state you end up in. I think that's very self-explanatory. And same thing here. The best state action pair in this state is equal to the reward you get plus the best state action pair in the next state. And you can see the difference is instead of dealing with summations or expectations, we're dealing with max now because you want the best. Policy iteration, this was what you guys did last week, where it's a method of finding the optimal policy, where you start with a random guess for a policy, you find its value function through dynamic programming and the Bellman equations above, and then you improve the policy by acting greedily with respect to the value function you found. And you repeat until the policy is optimal. And so this is a pretty interesting thing, right? So if you have an optimal value function, you can get the optimal policy via this equation. Whichever state you just sort of, see where the next reward is. You just pick the largest sort of value next state you can get, and that's the action you should take to get to that state is the optimal policy. And if it's the optimal state action value function, since the action is baked in, you already know which action is the best, so you just sort of pick that action. We'll see more of this later, but here's a question I want you to think about for right now. We'll talk a lot more about this very soon. But which one do you want to use for control, where control is the act of improving a policy and finding an optimal one, right? Which one? Just let that marinate a little bit. And Monte Carlo methods, now we did this really quickly last week. I won't go into this because we have so many things to talk about today, but does anyone, I think everyone's comfortable, right? Does anyone need me to quickly do a summary? No? Okay. Do a summary? Okay, fine. It's where you sort of, as I was talking to him before, it's where you sort of go to the end, right? You use the return as an update. And to get the return, you need to go all the way to the end of the episode, the terminal state. Now you're thinking, well, of course, well, you would use the return to, update your values and stuff, right? Because I mean, it's the return, it's the goal of reinforcement learning. What other methods are there? Like, what else can you use? Well, actually, you'll learn about something today called TD. That is a different paradigm, a different way of thinking, right? But in essence, Monte Carlo is a class of algorithms where you basically go to the end. You can think of it, end of the terminal state, whatever. Yeah.
I just also want to add on something that is really important here is that Monte Carlo, it is active sampling. So you're actively interacting with the environment, not knowing anything about it, and then you're getting sample averages and determining how good each state is through active samples.
And this is the update rule for Monte Carlo, meaning the current value function of this current state is equal to the return you get from this state, like the actual return, the experience, like your experience, minus your current estimate for the value function. Now, you can think of this as linear regression. Like when you're trying to fit a best fit line to a bunch of points, right? You try to sort of minimize this sort of residual, right, between the actual best fit line and the line and the best fit line, right? You might have a start with a guess for a line, and you might slowly shift it until the residual was very small between the actual best fit line and your guess. And it's the same here. You're sort of minimize the residual between the actual return, which is the value, and your estimated value. And you can see it's Monte Carlo because it has the G, it uses the actual return. And as Jessica said, this is a model-free algorithm because previously with dynamic programming, with these Bellman equations, you needed the model. You need to know where you end up at next, right? And sometimes you don't always know that. And so sometimes you just sort of brute force it in a sense. You just keep trying, you just throw yourself into the model or an environment and just try a bunch of crap and take the average, right? It's almost how you would estimate something, right? Just try a bunch of things, take the average. And that's basically what this is. All right, now, this is a very important section of the lecture. So please pay attention. So before I go on, right? We've been working with V so far, and I've talked a little bit about Q. Jessica has as well. But you might be thinking, okay, but so what is Q used for? Like, why are there two, right? Why is there a state action value function, state value function, a state action value function? Why is there a V and why is there a Q? And when should you use which, right? So now let's consider this, right? Assume this is a new environment, right? You don't know anything yet, and you're given this optimal value function for some, this optimal value function. Or it doesn't have to be optimal, just given this value function, right? The actions are up, down, left, and right. The rewards are -1 per time step. You're not given anything else about the environment, and you want to find the best policy given this value function. Now, what is the best action? Now, if you're following along the slides, you can look forward and see the answer, but I would hope you guys can think about this a little bit. What is the best action in this highlighted state according to this value function? Anyone have any ideas? Yeah, go ahead. Go left, right? Yeah, it makes sense, right? I mean, you have -14, right? It's negative, so the less the better. So you want to go to the 0, right? And it makes sense, right? But recall our discussion of policy iteration and our slides from last week, right? This was a grid world example we used last week, and I boxed these two things here, meaning that the agent cannot move the grid. This is what I boxed, and the fact that agent moves to adjacent square. We told you this last week. Remember, we didn't just throw in a grid rule. We had to write this stuff explicitly out. This was another example that was used last week. And once again, I box these two terms. Agent moves to its adjacent square, and the agent cannot move off the grid. Now you might be thinking, why the heck have I just randomly boxed some text on the screen, right? But given that I boxed this, and obviously I'm trying to bring its attention to you, what do you think? Do you still think the action is to the left? So to give you more of a hint, what about this? You look at this equation, right? I assume this is some value function. It doesn't have to be optimal, right? This is just the general way of redefining a policy. But let's assume you have like this equation. This is the equation you use to better a policy, right? Given the value function. Do you see what I'm getting at? Anyone? Remember, I've not told you everything about the environment. Do you know all the quantities in this equation? Is there something you don't know in the above equation? Can someone point it out? Yeah, go ahead. Exactly. That's the key here. You don't know P. You don't know this transition probability, right? You don't know the transition probabilities. And as a reminder to what these are, it's the probability after you take an action, right? You're given a state and an action. The probabilities you'll go to the next states. Here's an example. Here's a state. Here's an action. You take this action. You go to one of three next states. Now, it could be that you go to these states with a probability of 1/3, 1/3, and 1/3, or it could be, 0.1, 0.2, and 0.7, right? That is what the transition probabilities are. After you take an action, the model, or the wind, if you will, just in the environment, will blow you somewhere. And you don't always know what that is. I mean, how often in real life do you have an accurate model of the environment when you're doing a problem, where you're solving a problem? It's very rare, right? I mean, it's very hard to model something as unpredictable as the wind or just anything else. So, what is the limitation of using V? How do you know that going left takes you to the adjacent state, right? What if it goes here instead? Actually, that's preferable. Let's say it goes here instead, right? What if it goes here instead, right? What if it goes off the screen instead? What if it takes you to, like China or something? You don't know. You don't know. That's my point. You don't know about the transition dynamics. So you can't use the V, the value function, to gridify your policy. Does that make sense? Does that make sense? Right, because it could go left. It could go there. There's no difference. But yeah. Or it could, go off the screen. It could go anywhere. It could go to a state where the expected, the value is negative infinity. Yeah, go ahead.
Did you just say each step you can go to only adjacent square? Did you just say suddenly to go to?
I did, but where? See, that's the thing. I didn't say that. Right? Where did I say that? For this environment, I never said that. Right? This is why I made a point of saying I tell you nothing about the environment here. Right? That's the issue with the value function, in the sense that if you don't have the model, if you don't have the transition dynamic, it's absolutely useless to find a better policy. It's not useful at all, because you have no idea if you go left, you'll actually go left. If you go up, you can go anywhere. You can literally go anywhere. There could be 100 states you end up at. If you had the model, you could then take the average. You could figure out the probabilities and take the expected value. But here, you have no idea. So that's my point here. And that's a very big key, right, with the idea of the state value function. It's not that useful in the sense to find a better policy. Now, in real life, I'm not saying it's completely useless. I'm not saying that, because lots of algorithms use it, but not for the purpose of improving the policy, not selecting the next best action. I can tell you that. So now notice the equation here, right? What do you notice is missing from this equation and this one? The transition probabilities, the model. The value of all the possible next states are already baked into the Q function. I'll explain what this means later with an example. But because we have an action, we select an action already, all the possible next states, all that randomness, all that BS is already sort of incorporated into the Q value itself, the number itself. So this is what every single algorithm ever uses to improve the policy, to find the best action for a particular state, the Q function. This is why we need a Q function. This is why the V just doesn't cut it. Now you'll be thinking, okay, last week, why did we talk about V all the time? What were we doing with that? We used V, right? You guys were using V. Well, the answer is you had the model at that time. Remember in the notebooks that Jessica coded, you had all the transition probabilities. And Mithun, you had all the transition probabilities, you had everything. Dynamic programming methods for V that you did last week all had the model. That's why we were able to use it. But in most situations where you don't have the model, and that's most situations, you need to use the Q function. Very important idea, please keep that in mind. So now, this is a different grid rule. I know it's not the best sort of parallel between the first one and this one, but let's assume you have this environment, right, this grid rule. You're given a Q function, the actions up, down, left, and right. You're not given anything else about the environment. What are the values what are the best actions in the highlighted states, right? So that state up there, the top one, what is the best action? Yes. How about this one? Yes, exactly. Very simple, very simple. Now I'm thinking, okay, so then why is it that V needs the model and Q doesn't? First of all, I want you to notice, if this were V, right, there will only be one number per square. But there are four, one for each action. Because remember, we're dealing with state action pairs. So each one needs a number. So you can think of V as a sort of amalgamation of these numbers, right? This sort of, like, it sort of encompasses all the possible actions in a state. Whereas Q explicitly specifies a value for each action. This means that, going back to the diagram of the transition probabilities, it's sort of already considered the fact of like all the possible next states. Do you guys get that? Like, it's the fact that you have already picked an action, and that action has already led you to like the next state. So if you have that number there, right, whatever it is, 0.63 or whatever, you know that is already considering all the possible next states it goes to, because you've already picked the action. Whereas for V, right, you get a number, -14. You don't know which like action that corresponds to, like which action led to -14. Maybe one action was -100, one action was +5. You don't know which one it is, right? So this is why the Q function, you don't need a model, because the action, all the possible next states, everything is already baked into that number there, 0.63, right? I hope you guys can sort of intuitively see that. If not, just I can clarify. But yeah, so you don't need the action here, or rather the model here. You just pick the largest state action value. Very simple, very simple. And this is what every single reinforcement learning algorithm ever uses to better the policy, to find the best action for a state. No, it's not that you can't use V, or nobody wants to use V, it's that you can't. It's impossible. Without the model, it's impossible. So we talked about Monte Carlo methods with the value function last week. But now, what about Monte Carlo methods with the Q value? But first, before we get to that, this is the sort of workflow for policy iteration, right? You start off with some random value function, some random policy. You find the actual value, and then you act legally with respect to the value to improve it, etc., etc. Does this work with Monte Carlo? Does this work? Yes. Does this work? No, it doesn't. Why does it not work? Which of these two steps breaks? Which one breaks? It doesn't work. I can tell you it doesn't work. Which one's the problem? Policy improvement or policy evaluation? Which one makes it so that you can't use V for Monte Carlo?
It's something with the environment.
Right, go ahead.
I think it should be policy improvements.
Perfect, exactly. Because, as I just told you, you cannot select the best action. You cannot gridify your policy with respect to V without the model. Monte Carlo is model free, so you can't improve your policy at all if you use V. You need to use Q.
Or maybe not using model, I think you don't know how the environment is structured, so you don't know where it's going to take you next.
Yeah, you don't know where you'll go next. So I mean, it's a situation I talked about just now, right? You don't know if going left will take you off the page or anywhere, right? To space, whatever. So you can't use V here to improve the policy. But, right, because the model is right there. You need the model. Once again, this is a very important concept, so I'm gonna reinforce it many times. You have the transition dynamics there. You don't know what the environment does. But for Monte Carlo control, if you want to do this sort of policy iteration framework, you need to use Q. And this works, because as you saw before, you don't need to know anything about the environment. You just pick, in each state, you have a certain number of actions, let's say 5, 10, 15, 20, whatever. You just pick the one with the largest Q value. Simple. Now, how do you do policy evaluation with Q function? Because, before you've done policy evaluation with the V function. Recall that this is the Monte Carlo upstate with the value function, right? It's the same. Recall the definition of the Q function. It's just almost the same as the definition of V, but this time you have to consider the action. And what is this quantity here? It's just G, right? It's just the return. So actually, nothing changes pretty much. You just, instead of using V, you just do this, right? This is one thing, as Jessica said, is random sampling. You start in a random state action pair, right? You don't know, maybe square one going up. You take a step, you take the action, you go to the next one, you randomly sample a state action pair from the next state, and you just subtract, and you keep going, you get the return, and you just do this. All right? So I hope that clears it up, why there's a Q function, why there's a V function. And I really hope you guys remember the key idea, that you want, to get an optimal policy, you need, or you don't need, but a lot of algorithms use an optimal Q function. You can't get an optimal policy from the optimal V function if you do not have the environment dynamics. Yeah, go ahead.
Are we assuming that we know the values of actions since the beginning?
That's a good question. It's the same thing as you would do for V, right? Remember how in V you initialized your V function with all zeros or some random value? It's the same here. You just initialize each state action pair with a random value, right? Maybe zero, all zeros, right, this time. But it's just each state action pair instead of every state. Yeah. So then you keep doing it, Now you might be thinking, I'm going through Monte Carlo kind of quick. You might still, yeah, you have a question?
Yeah. What was the G function in the slide before?
G, yeah, right, because you missed the first part. It's the return. It's the total return, the reward you get.
Total amount of reward at the end of the episode.
Yeah, total amount of reward at the end of the episode. You take 100 steps, you get one value of reward for each of those steps. You add it all up. And this, okay, I'll go over this later, maybe, but okay. TD. Now, we've been talking about Monte Carlo a lot. Let's switch it up a little bit. This is the expression of return. It's as you can see, it's just the sort of sum of all the rewards, but with the discount factor, if you guys remember what that is. But notice that you can write it as the first value of reward plus the return from the time t plus 1, right? Because this is just the return from time t plus 1. I hope that's obvious to everyone, right? It's just you're sort of collapsing all the last terms into the return for the next time step. Make sense? Therefore, we have that, and this is the definition of the V function, if you guys remember. It's just the expected return you'll get from this state. You substitute in that value here. And what I'm trying to get to here is, and this is kind of similar to the Bellman equation, you can rewrite V as the reward you get from taking this step, plus your estimate of V at the next time step. Right? I think this makes sense, right? It's sort of Monte Carlo. It's sort of like Monte Carlo. I mean, not Monte Carlo, it's sort of like the Bellman equations, but sample-based this time. And this is something called bootstrapping, meaning that it's just, once again, the idea of writing your current estimate for something in terms of the next estimate for something. Now, this was the Monte Carlo update, and we used the entire return where you go to the end of the episode. But what you can do is you replace the value function with, the bootstrap, you can replace the return with the bootstrap value function expression. And this is called TD in the sense that you don't go to the end of the episode and get all the rewards and everything. You just go one step and use your estimate for the next value. You will see an example of this. But this is essentially what the TD error is and what the TD update is. Does everyone see the difference between Monte Carlo and TD? Everyone see it? Good. Please, if there's a question, please ask. And this is the key here, the difference, right? You have G and the TD error, or rather the TD target here, which is the return plus the value of the next state. And TD is model free. Why? Because in dynamic programming, we looked at all the possible next states, right? You had that model so you could sort of step through where you go next, each one, and then do all of that. But here, you just only need one next state. So you don't need the model, it's a sample-based method. So what you do is you start in one state, you take an action, you have no idea what the model is, so it doesn't matter if you go to space, you go to whatever, you still have a value estimate for the next state, right? So you use that instead, you just use that. You don't care about what possible state you could have reached, you just care about where you landed up. That's why you don't need a model. And TD is a model-free method just like Monte Carlo. Except that Monte Carlo didn't care about the model because it just kept going, right? You just keep going, you don't care where you end up, you go here, 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 you reach the end and you use that for the update. TD, you go once, stop, use your estimate for the value here as the update. So basically, I mean, this is sort of repeating what I said. You start in a state S0, take an action A0, receive some reward R1 and land in next state S1. And then you stop. You have a value estimate for the state S1, and you already have all the quantities you need for the value function update. You take the value of S0 plus some step size, the reward you got, R1, plus the value at the next state, so V of S1, minus V of 0, S0, right? Yeah, you keep doing this. At S1, you do the same before S2, etc., etc., etc. Right? And it keeps going until you reach a terminal state. Or sometimes you don't reach a terminal state if it's a continuing task. Let's compare the updates. What algorithm is this? Which one is this? Which one is this out of the three? Monte Carlo, TD, dynamic programming, which one? Yes, right? Why? Because it goes to the end. You go to the end before you make the update. What about this guy? What is this? Monte Carlo, TD, dynamic programming. Yes, exactly. Because you look at all the next states. And to know, once again, I'm going to rehash this point again. You need the dynamics model, you need the P. Because after you take action, you need to know which state you end up at. And finally, this is TD. You can see the difference, I hope. Unlike Monte Carlo, it doesn't go all the way to here. You just stop right there before you do the update. And unlike dynamic programming, you don't need to know the dynamics because you just randomly go to one of the next states and then you use that. Pretty clear? All right, good. Yeah.
The TD one, then what is the next step? We take another action from ST plus 1 and then like keep going?
Yes. There's an example I will show you.
Oh.
But yeah, so you go to ST plus 1. The black dots are actions. You take one of those actions and then you end up one of those states, these four here.
Yeah.
And then you repeat.
I see. And when we reach at the end of the state, are we going to go back to S of T again and redo that?
Yeah, sure, yeah. Because this is sample-based method, right? You randomly, at each state, you just sort of keep, it's like Monte Carlo, you keep going. If you do this, like Monte Carlo, let's say, you sample an infinite number of trajectories, you keep going, let's say, eventually you'll converge to the actual value, right, or Q value. Here's the same, you just keep going. Like once you reach the end, you keep going again, you reach the end, you keep going again. But I'll talk about this later, but for now it's just, you keep going.
So one last thing, so is it correct to say we're enhancing each state once at a time? Like kind of thing. So for example, initially we're like trying to improve the state of T, then T plus 1, then we keep going until we go through all of the states.
Basically, You can kind of say you start off with this S of T, you improve the value estimate for that, you go to ST plus 1, improve the value estimate for that, you keep going. Monte Carlo is, I mean, you can sort of do that as well, Monte Carlo, but this is more pronounced, right? Because you only take one step. And this is just the algorithm, it's sort of algorithmically-fied, in this sort of fancy font. But it's basically what I was talking about, right? You initialize some random value function, right? And then for each episode, like however many you want to do, you pick a random starting state, you take an action, do this, right? You have this means S prime means the next state, right? you have a value estimate for the next state, and then you sort of do the update, and then you update the next state to be the same, just keep going. Very simple. This is what I've been talking about, but just in a sort of fancier, more formal way. So now, you might be asking yourself, okay, so you got these two paradigms, Monte Carlo and TD. One is long, one is short. Which one should be preferred? Let's look at these two things here. Now, the top, the return, is used in TD. It is used in Monte Carlo. The second one, the TD target, is used in TD. Which one is a better estimate of the value function? Which one is like a, because these two are sort of trying to represent the same thing, right? The value function. Which one's a better representation of the value function? Yes, right? Why? Because, I mean, you can see GTG, like the value, that is literally the definition of the value function, right? The expected return starting to state. However, this is an estimate, right? Let's say your estimate for the value of the next state is very inaccurate. Then your estimate for the value of this state will also be very inaccurate. Does that make sense? So it's like not, it's sort of, this is more of an estimate than that one, because GT is actually the value. I hope that makes sense to everyone. Which takes longer to compute though, the return or the TD target? Which takes longer? The return, right? Because you have to wait. Whereas the TD target, you can do it right away, one after one step. Oh, this is a tricky one. Which is lower randomness? In the sense that you don't know the model, you don't know the dynamics of an environment, right? So every time you take a step, you're almost like, you know, throwing yourself into unknown, right? It's like you don't know where you'll end up because you don't know the model. So out of all of these, which one has more randomness? Like how, like, yeah, which one has more randomness? Go ahead. Exactly. Why? Because you're taking multiple unknown steps. Every time you step, get RT plus 1, RT plus 2, RT plus 3, you're stepping into like an unknown environment, right? Because you don't know the model. You keep stepping. But here, in the TD target, you only take one step. So there's much lower randomness. So which do you prefer? I mean, there is a correct answer here, but I just want you to think about it, right? It's okay, like you guys can think about it. Which one would you prefer? Do you prefer a better estimate of value function that takes longer and has more randomness? Or do you want a less accurate, but takes shorter time to compute and has lower randomness? Which one? Like personally, right? When I first heard about it, I'll tell you about me. When I first learned about it, I mean, accuracy, right? I want the Monte Carlo update because it's more accurate. I mean, it's literally the value function. Now we'll see if this holds up later, but here's sort of the summary here about the TD versus Monte Carlo. TD works for both episodic and continuing tasks. Remember what these are. Episodic tasks have a terminal state. They end. Continuing tasks never end. They just keep on going. Like maybe you're like, let's say, monitoring a power plant or something. It updates immediately, does not wait till the end of the episode, what I've been saying. Has higher bias, meaning less accurate estimate of the value function, but lower variance, randomness, because it takes only one step of this unknown environment. Monte Carlo only works for episodic tasks, meaning you need a terminal state, otherwise you can't compute the return, right? Because you need that thing needs to end. It waits till the end of the episode, but it has lower bias, it's more accurate because it literally is the definition of the value, G, right? But it has higher randomness because you need to take a bunch of like random steps, higher variance. Just a summary. And when I first heard about this, I was like, okay, sure, like whatever, like continuing task, whatever. I was focused on the accuracy part. I was like, okay, it's more accurate, right? It's pretty good. Well, let's actually do some computations because you know this is all abstract. Let's say you're going home and you want to estimate your value. Maybe the time you take it gets home. You take to get home, and you have the states here: leave, exit highway, whatever. Let's say you know this is what actually happens, right? You estimate it'll take 30 minutes to go home, right? And then you know you leave. It takes 5 minutes to exit your like workplace. So now you update your value to 35. Like you think it's 35. Actually, no. Excuse me, no. This is like the reward, right? You like get 5 reward here. So now it's sort of 35. It takes you 15 minutes to exit the highway, right? You think, okay, maybe now I'll take 15 minutes to get home. But then it takes 10 minutes on the secondary to get to the secondary road. Now you think, okay, it'll take 10 minutes. you'll take 10 minutes enter the home street, and I think it'll take 3 minutes to get home, and you'll ride home. And here is like the sort of total time. Right, actually took 43 minutes. Right, you can think of this as almost the total return. So let's start with Monte Carlo. The total return starting from that state is 43. Right now, this is kind of like contrived because ideally, return at the higher the better, but you probably want to get home faster, but whatever. So there's a total return of 43, right? And so the value of the first state is 30, which is the value estimate for that state, plus 43 minus 30 equals 43. And you can see how good of an estimate for the value the Monte Carlo estimate is, right? Because you can see it's, literally the definition of the value. Very good. You do the estimate and it's 43 right away. You can see that it took you 43 minutes to get home, you get a value of 43, right? Doesn't really get why this is Monte Carlo. You wait till the end, you get home, you calculate how much time it took, and then you do it. Make sense? Now what is the value for G1, right? So G1 is that node of 35. So as you can see, you've updated your value to be 43. Now for G1, it took you 15 plus 10 plus 10 plus 3. So you can see here, this is the total return starting from G1. And you do the same. You update it again, and it's 38. Oh wow, very good, right? Because it's the actual, once again, Monte Carlo actually is the value. And so as you keep updating, this is like the updated values. And you can see it matches exactly how long it takes to get home from each of those states. Perfect, Monte Carlo, right? You have to wait till the episode to terminate to do the value estimates, right? Because you have to get home first to know what the total return is. Now what about TD? What happens here? Okay, you don't know, like this is the same situation, but let's assume you don't know, you haven't traveled, like exited your workplace, so you haven't went to the highway yet. But notice that even without that, you can update right away. The value of S0 is 40, right? Because you've already experienced one step in the environment, and so you can update right away. Let's continue. So, okay, you updated your first state. Now it's time for the second state, the 35 state. And it took you 15 minutes. You took one more step, received the reward. It took you 15 minutes to exit the highway. You plug it into the equation, right? And you get 30. And I haven't sort of updated it here, but you can see the idea, right? And does everyone see the idea, the difference between Monte Carlo and TD? But you can notice that it doesn't quite match with your final time, right? Because it's 40, it's 30 here. It's not that accurate, but it's fast. It's fast. But let me tell you this, and this came as a surprise to me. In practice, I think pretty much all of the reinforcement learning algorithms I know, almost, they use temporal difference learning. Why is this? Can someone maybe this is a hard question. Even I'm not 100% sure, but obviously it's not always, right? Sometimes you want to use Monte Carlo, nothing's universal. But a lot of the reinforcement learning algorithms, especially the state-of-the-art ones such as PPO, SAC, they pretty much prefer TD over MC. Why is that? Any ideas? Go ahead.
It's not an answer to your question,
Sure.
but I'm still wondering what exactly does the number itself.
Sure, it's sort of your estimate for how long it takes to get home. From that cell, yeah. Maybe I should explain.
Monte Carlo, it started with 30. We started with 40.
We didn't start with 40 here. We start with 30 here. 40 is your estimate. After you've taken one step, you plug it into this equation. You update your value estimate right away. So it becomes 40, you can see it, right? Yeah.
So how come you know the second cell already when you're only in the first cell? So in the gamma E ST plus 1, how did you know that number before you reach
Right. So what you do, say that again. Wait.
Gamma E ST plus 1, right?
Mm-hmm.
I think before this is TD out.
This is TD, yeah. Yeah, so what would normally happen, this is once again not the semi-contrived example, but usually, let's say you have a grid world and you were here last week, you remember, you randomly initialized all of the states, every single state. Yeah, so if you're let's say you have a grid world of 16 by 16, you have 16 states. you would initially begin at the beginning of all the algorithms. So let's say, for example, let's go back really quick. You see this term here, these two words here, initialize V of S. If you have a 16 by 16 grid, you initialize a random value for every single one of them. So that means you start at any random state, you go to any next state, you already have that value. Do you see? It's because of the initialization. Yeah. And it's the same for Q. Let's say we're trying to estimate Q instead. You initialize a random value for every single state in action pair. Or see that? So yeah, so you would already know, yes. I mean, yeah, you would already know.
So the 30 minutes is arbitrary?
Yeah, it's arbitrary. It's just an example, right? How long it takes to get home. I really just want to get this idea of Monte Carlo versus TD across, where this is the total return you get from this episode, right? Terminal state is your home. Monte Carlo, you have to wait till the end, and then you can update. But you can see the updates are pretty accurate. Whereas for TD, you start with 30, and then you can already update, given your reward, right? You need to take a step first and get the reward, and then you can update. You can notice the rest of the little circles are still blank. You don't know what they are yet. Or not you don't know what they are, and you don't know what the rewards are yet, right? Because these lines are blank, meaning you haven't received the rewards yet. So, but you can still update right away, whereas Monte Carlo, you have to wait all the way.
So if you guys remember from last week, our value function, we started off with most of them we started off with all zeros. So that's like the initializing step.
Yeah.
In this case, like our first initialization for the first value, we just randomly picked.
Yeah, we just 30, and then technically, if you really want to be technical about it, for TD, all these circles should have some random value in them. But for the sake of illustrating that, you don't have to know anything about your returns and the time it takes to get home. I sort of left them blank. But yeah, you would initialize all your states with some random value before you start. I hope that makes sense. Go ahead.
If we initialize the values with completely random values, how do we know that the values that we got from TD or Monte Carlo is closer to the actual value? Because it's determined by the values that we randomized.
Exactly, that's a very good question. Because you'll get a return. If it's for this case, once you reach the end of the episode, you'll receive rewards. These rewards are actual things from the environment. They're like the actual things you want to estimate. Once you reach the end, you'll receive these. Actually, you don't even need to reach the end. By receiving rewards from the environment, you will gradually, because the rewards you receive are like the correct values, you see, you will eventually get your estimate better. Yeah.
Can we get a local variable?
Oh yeah, of course, definitely. But that's outside the scope of this course. In deep reinforcement learning, there's lots of problems with getting stuck in the policy. There's so many things like that. All the problems in machine learning and optimization generally will happen in reinforcement learning. It's not like some protected algorithm class, right? Yeah. But does that answer your question? Both of your questions?
Can I just ask you?
Sure.
So are you seeing that? So is this grades where you have to go several epochs in it?
Yeah.
On the word function you get when you update?
Yes. Yeah, so because you start, this is without the model, right? What you do, it's a very almost, you can say like a brain dead method. You just start off, right, with some random values. You have no idea what they are. You just keep trying stuff. You should keep taking actions, get rewards, boom, boom, you keep going until the rewards you get sort of override those initial estimates. It gets more and more accurate. Because reward is what you want to maximize, what you want to know. As you take more steps, you'll understand which states have higher reward, which states have lower reward. And this will eventually lead to better and better value estimates. And if you remember policy iteration from last week, I don't know if you're here, it's a iterative process. You start off, make it better. Yeah.
Let me just add something really quickly. Monte Carlo, you're going to be, you need the entire episode to be able to do your updates, while TD, just to hone it in a little bit more, TD, you can do these updates as you're stepping through your environment. So with Monte Carlo, you need to simulate everything first, but with TD, I can take one step, go to a different state, and do the update. Take another step, update.
Yeah.
Monte Carlo, you gotta walk all the way through.
Yes. Does that make sense? Good. Now, I'm not to spend too much time on this, but I think it's kind of important. TD is better than MC in most cases, and pretty much all cases actually. Can someone, this is kind of a hard question, but can someone tell me why? What do you think? What do you think? Why is that? Yeah.
Because we can get stuck in a local minimum, so we use multi-color. It's a better estimate of the variable, but it's like because it's too accurate, then we can get a local thing. It's the same thing as why stochastic gradient descent is better than normal gradient.
See, Monte Carlo is an unbiased estimator of, or let me not talk like that. Monte Carlo is actually the return. So, do you think, would you get stuck in a local minimum? I feel like if you use Monte Carlo, you will reach the actual minimum. And let me tell you this. If you do infinite episodes of Monte Carlo estimation, there's a 100% chance, it's guaranteed you'll reach the actual value function. You'll reach the actual correct value function. That sounds pretty good. Whereas in TD actually, it's mathematically proven, even if you do infinitely many episodes, you'll never reach the minimum. You'll converge to something called, I forgot what it was called, but you won't actually reach the minimum because it's a biased estimator. It's an inaccurate estimator of the value function. But why is it that TD is preferred? It's because in reinforcement learning, variance, the concept of randomness, variance, basically trumps all. The more random something is, the less likely it is to converge. Monte Carlo has a crapload of variance. You wait till the end of the episode. You take, some episodes are 1,000 steps or 10,000 steps. Each step, you're stepping to an unknown environment. This sort of, you don't know the model. So it like goes back and forth. It's crazy random. However, in TD, you only take one step. And variance makes it so that your algorithm will not converge. It will diverge your algorithm, right? Because let's say, you're taking some steps and randomly, like in a Monte Carlo episode, you just walk off a cliff, right? Because it's random. And that's bad, because then your learning is doing well, and then boom, it just crashes, and maybe it never recovers. But in TD, it's little incremental steps. It's little incremental steps, less variance, and each step you're making the value estimates better. So it's less variance, your algorithm is much more likely to converge. Yeah.
Didn't you say Monte Carlo is guaranteed to?
Yes, but it takes too long. Yes, but in practice, like if you have infinite time, infinite computation, yeah, it'll do it. It'll do the job.
Compute is very expensive. I'll say that.
Yes.
Oh, so it's
But
very-
in practice, yeah, TD, it will get to the value after you solve a problem with TD. It's not the actual value function. Sorry guys, it's not the actual value function, but it's good enough. It's good enough. You see, you get me. Well, I can elaborate on this later, but I kind of want to move on. But basically, remember that variance is the bane of all existence in reinforcement learning. Almost every, like later on, like the more advanced methods, policy gradient, like everything, they do stuff to minimize the variance, to prevent randomness. Because environments in reinforcement learning are very random, and they're very hard to navigate. TD for control. Now, I was talking about TD with values all the time, right? But can we learn the Q function with TD, right? And as you remember, you need the Q function to get the best policy, of course. Just like how you use Monte Carlo for the Q function, you can use TD for the same purpose. And what is this? So I want you guys to change the paradigm a little bit. We've been talking about state value functions so far, but I want you to think about state action pair to state action pair rather than state to state. So let's say you have this rat or mouse going to this cheese. Right? State to state is this. This is V. You consider one number for each of those states. But for state action to state action, and let's assume, of course, let me just define the environment for you. Let's say in each state, you can go left or right? So then, you have to start thinking about state action to state action. So each grid would have two numbers associated with it rather than one. And then it's simple here. This is the update for the Q for V in TD. What is the update for Q? And here we're getting to some actual practical algorithms because you can actually use it and it will converge with low variance. SARSA, what is SARSA? SARSA stands for state, action, reward, next state, and next action. Or the components that go into the update, the things you need to calculate the necessary quantities. So, very simple. State, action, reward, and let's assume for this environment the reward is 0 for each transition, except at the end where you get some positive reward. Next state, but you also have to pick next action. If this were V, if we're working with V, we ignore the next action. We just go with the next state, right? But now we also need the next action. So once you're in the next state, you need to select the next action first, right? And the next action is just sample from the current policy. So this is the update. Very similar to TD for V, but it's just using Q instead. I hope everyone sees that. State, action to calculate the current Q value, the reward for this thing here, the next state and next action to calculate the next Q value. And once again, to answer his question, you initialize a random Q value for each state action pair, so you would not know it. Very similar. So an example, uniform random policy, so 0.5, 0.5 for each direction, alpha equals 1, and gamma equals 1, where alpha and gamma are those step sizes there. You start with a state action pair. Let's assume that you start in the state 2 and you want to go right, and assume this state action pair, not state action pair has a value of 1, reward is 0. You go to the next state action pair. Let's say, but you'll definitely go to 3, right? Let's assume that's how it goes here. And then the next action is you go right, you pick randomly. So I could have picked left, but I just picked right here. And that Q value is 2 because it's closer to the cheese. And yeah, so it's randomly sampled from the policy. And you do the calculation. So the Q value of this state action pair is simply the Q value of this state action pair plus 0, which is the reward, plus the Q value of the next state action pair minus the Q value of this state action pair. So it's 1 plus 0 plus 2 minus 1 equals 2. SARSA. And now it's we're just going to take over. Yeah, so just before we do this, it's just keep in mind what we talked about here. Q values, all right? State action pair to state action pair. Before we were working with state to state, now it's state action to state action.
Yeah, well, thank you, Jingmin, for.
I'll be back, by the way, don't leave. There's more juicy stuff.
So, I guess this is the pseudocode for SARSA. So, just to remind you of what that stands for: state, action, reward, state, action. So this is going from one state action, get a reward, going to the other state, going to the next state action. So essentially, what's happening is that first things first, what you do. Again, you're stepping through an episode actively. So the first thing that you do, well, you just gotta choose an action. You just gotta choose an action somehow. And once you have this action, then this is your update. This is your queue update. And once you update your queue, then you use this again to perform epsilon greedy. Oh, sorry, that was a little preview of next. And if you guys go to the Discord, in the channel I sent, or if you go into your emails as well, I sent the slides, or not, what am I saying? Okay, I sent the notebook, a copy of the notebook. Yeah, so like I already made a copy of this. So I'll let you guys, I'll give you guys a little moment to do that. Yeah, if you it's in the Discord server UT, and then go under the section UTMIST academic events, and then it's in the channel RL workshop. And as you guys are doing that, I'll just talk a little bit more about so general reinforcement learning. So we generally use this library called Gymnasium, which is kind of like your one-stop shop for all reinforcement learning environments. So here originally it was developed by OpenAI, but then like they stopped supporting it, and now it's kind of open source, run by our open source community. And it just has like a lot of different, it just has so many different, cannot spell. It just has a lot of different environments. So like you have everything from, let's say, Atari games. Okay, it looks like they have a new website. Oh, oh wow, okay, they updated the arcade learning environment. Okay, well, you have everything from Atari games to like classic controls. So this might just be your basic reinforcement learning, what are these called? Like baselines, just to see if your algorithms work. And the ones that we're going to be using today is it's a toy text environment. It's cliff walking. So essentially how cliff walking works is that it might be a little bit more clear here. So we have this environment, discrete environment. So the state's like clearly defined, not continuous. And you have this giant cliff. If your agent walks into the cliff, you get a reward of -10. And then you get thrown back to the start, which is this state right here. Until you reach the goal state, you get a reward of -1. And when you reach the goal state, your episode terminates. So essentially how Gymnasium works you guys can follow along and render this as well. Here I don't, so if we look at, actually this I don't have in the, this I just coded up a little bit earlier. But let's just see what's going on with Gymnasium. So here, I just put a wrapper around the environment so that I can make a video. And here we are stepping through the environment. So right now I just selected a random action just to demonstrate. In our environment, in env.step, we pass in this action, and like the environment knows what state you're in. You take this action, it will bring you to a next state. So in this case, our actions are just up, down, left, right. And then what's being spit out, it will be the next state, or like observation. Here the states are discrete, so we'll just call it state. Your reward. And then the next ones are just a little bit of extra information. So terminated tells us whether or not the environment, or not the environment, whether or not the episode has terminated. Do these lights not turn off? Okay. Yeah. Hopefully that's a little bit more clear. Truncated info not important right now. Terminated basically tells us if our environment or our episode has terminated, so we can restart another one. So then, like you can kind of.
Where was that clip that we were showing?
Sorry.
Where was the clip that we were showing?
This one's not in there. It will be at the bottom. This one I just coded up really quickly just to demonstrate a little bit. It will be used later, or like it's already coded later. So it's just like, well, the agent is just kind of doing random actions, walking through. But yeah, this is essentially Gymnasium. This is one of the environments in Gymnasium. Yeah, and then, yeah, as you can tell, this is with 60 frames per second. The agent isn't doing really well with random actions, so let's try to fix that. Actually, let's just let that run. It's a minute long. But yeah, so the next thing that we have is our Sarsa agent. So here, again, written by Mithun, did a really great job with this with these notebooks. So first things first, if you recall in our, if you recall, we have to choose an action first, and most of the case, epsilon greedy. So let's just, do you guys remember how epsilon greedy works? Nope. All right, so if you remember epsilon greedy, epsilon is your probability of exploring. It's your probability of choosing a random action. So if we just start off with, here, let me just double check. So this one I'll walk you guys through. So we have to first get a random number. We already have epsilon defined over here. So, and we also have a random number generator that we already pre-seeded. So seeds basically, seeds will help you get reproducible results. That's the basic idea of it. You'll probably be a little bit more familiar with them like as time goes on. But your random, let's just use the random number generator that our agent already has. So self.random, what is it? Oh, no, rand generator, my bad. And what we want to do with this, it uses np.random, so we can just straight up use the function rand. And this will give us a random number between 0 and 1. And then we only want to explore if, or like epsilon, yeah, if it's smaller than epsilon, exactly. So we already have epsilon defined. So here, we want to explore. So we want a random action. So, and then we're going to use a random number generator again. And this time we are going to use the random integer because like our actions are integers. It's they're encoded 0, 1, 2, 3. And then here, we can just use self.num actions. Num actions we defined over here. Because like in each state, you can take the same number of actions. All right. So this is our exploration. And now let's do our greedy. So here we are exploiting. So, well, you want to get the max value, correct? Always big enough. Yeah, that's a little better. So you just want to pick the best action possible, and how you do that, you just pick the action that gives you the max value. So let's just call it, I can't type, let's just call it max value. And then np.max gives you the max number of an array, or an array of integers, not integers, just an array. So we can do, we have this predetermined values, or like state action value over here that we can use. So self.action values. And how this works is that we need to pass in a state which is already given to us. And so what this does here is that we have a state, and then for each of our, sorry, how this is structured is that each row is for a different state, and each column is a different action. So if we just index it first, then we get our state, and then passing in this colon over here just gives us the rest of it, just gives us that row. Yeah, and then so this gives us our max value. So this is our best value. And then next we need to find our indice, or we need to find the index. So let's just call it max indices. And np.where is a function, or you can kind of read it here. It passes in an array of elements, and then you also pass in a condition. So our array of elements is going to be this, or our action values. Same thing, we still want to stay in our state. And then, oh, my bad, whoops. And then let's just, we want to make sure that these value, you're only grabbing the indices that equal our max value. So this is kind of like our argmax. Oh, why is everything, okay. And let's just grab the first element of this. So np.where will return an array. This is like, say, might be used for, let's say, if you're if two states have or two of your values of the array have the same action or have the same value. So this just kind of grabs the first one. And now we can finally determine our action. Oh wait, sorry, wait. np.where it doesn't return an array, it returns an array of an array, so it's a little bit nested. That's why we have to use it. Sorry, there's too many numpy functions. So actually what max indices gives you is like, it gives you a list of the indices where or it gives you the argmaxes. So now we can use our generator and we can use this function called choice that just gives a random, it just samples from our list of indices. Yeah, sorry about that. Yeah, so here is our sample. Yep. So here we're, yep.
I'm a little bit confused. So for exploitation, are we supposed to choose the state with like the highest value?
Yeah, so what if two states have the same value?
So max indices are storing like the indices of states that have the same value.
Yeah, so whatever has the max value, it just grabs that. Yeah, so it's kind of like an argmax. Or but in this case it takes care of the situation where two states might have the same value. So that's why we have to do the random choice at the end. Yeah, sorry if the explanation was a little bit iffy. Yeah. So this is our epsilon greedy.
Hi everyone. This is Jessica from the future speaking. I realized I didn't really do a good job of explaining a lot of this how Sarsa and how Q learning works with the code. So I'm here going to just uh, re-record this section on Sarsa explaining the code, and hopefully that helps you understand Q learning as well later. Oh, I guess like at this point in the recording, you haven't touched on Q learning yet. That's a little bit of a preview of what's next. Um, but yeah, let's just look at Sarsa one more time before actually jumping into it. So an we have a loop for each episode. So if you recall, an episode is just like a pattern of state, action, you get a reward, you go to the next state, and then you choose another action from there. So the first thing that we do in these episodes, well, first of all, you have to initialize your queue function. And remember, we're always going from state action pair to another state action pair. And that's where the name Sarsa comes from. So you initialize this, and then you start with a state. And from this state, you first choose an action, and that's kind of what where did that function go? Our agent start is doing. Agent start passes in a state. you choose an action, and then this will come into play later where we need to record our previous state and our previous action to actually perform the SARSA update properly. I'll explain that a little bit later. Um, this part is pretty important, so just bear that in mind. How we choose our actions is that we just keep using epsilon greedy. If I ordered, if I reorganized these this video properly, we should have already done this a couple of minutes ago. But yeah, I'll just go through a little bit more of the what's in this agent for now. So epsilon, that's your probability of exploration. Oh, there's a little typo here. Yeah, this is your probability of exploration. Step size, that is this alpha over here. This is pretty much how much you want to update your previous value by. So it's like if alpha is 1, you want to update it by this entire value. If alpha is 0, you just straight up don't update it at all. Discount is your gamma. So typically we have step size as alpha, and discount is going to be your gamma. And then this random number generator we used earlier when choosing our action. So this is pretty much just a generator that like will give you random actions or random numbers. And I believe I might have explained this earlier. When you seed something, if you use the same seed, it will give you the same results every single time. So therefore, you can like test to see if your code is, let's say, reliable, if it's giving you the same information every single time. It also really helps with reproducibility so that if someone runs your code with the exact same seed, they should also have the exact same results. Next, action values. Also should have explained earlier, this is your Q function or your state action values. So how this is structured is that you have it's a nested array. So you first have your array, or it's a nest, and then each row is going to be a state. Each row represents a different state. And there are 47 states, I believe, or there are 48 states. So you have like yeah, there are 48, imagine 48 of these. And then for each column, it's your it represents the action 0, 1, 2, and 3, which is, let's say, I believe action 0, like it goes up and then right, down, left. I'm not completely sure. But what's important here is that each entry corresponds to a state, so the row, and the column corresponds to the action. So let's say if I index this at 0, 0. This gives me state or the Q value for state 0 and action 0. But let's say if I indexed it at state 10, action 2. So this is going to be the Q value for the state action pair 10 and 2. So hopefully that clears things up a little bit. Um, what's next? Yeah, this is just initializing it. Here, yep, I explained a little bit earlier that we're going to be needing the previous state and previous action when doing this update. And the reason is because if we go back to the pseudocode, so we initialized everything, we kind of know what the states are. Next, first up, we have agent start. So we already chose an action from our starting state using our Q value. So we're using the epsilon greedy policy. Oh, whoops. Yep, there we go. Oh my God. Sorry. And then we take steps inside our episode. So, first things first, we're currently in state S, and then we uh, get a reward, and we go to a new state, S prime. And from S prime, we have to choose our next action. So from S prime, in our new state that we're in, we choose a new action, A prime, and when we loop back, this is what becomes A. This state and action update will come in play later. So we choose a new action A prime, and using this, we update our Q values. And how this works is that, um, like in this, just looking at this, it looks like that we need to maybe look ahead to see, or we need, when we say next state and next action, it sounds like we're looking into the future. But in reality, we can't really do that. And that's why we need previous state and previous action. So in this case, we're kind of shifting everything back. Instead of looking, let me just write this down. So instead of looking forward, instead of looking forward for the next state and next action, we look back to our previous. And this is why our previous states and previous action is kind of treated as our S and A. So right now, you might have the mindset of like, oh, currently we're S and A, and we want to look at next S prime, next A prime. But take a step back and think of it as S is your previous state, A is your previous action, R is a reward that you get from going from this previous state and taking this previous action, and S prime is your current state, and A prime is your current action. Think of it that way. Um, so let's write this down. Instead of state here, current S, current A, R, next S, next A. Let me make these primes. So this is what you might be thinking right now because we keep saying next step, next state, next action. But in reality, let's take a step back and think of it this way. Previous state of action are current. S prime current. Now hopefully this makes a little bit more sense. It's like how when you're tr if you've taken some computer science classes or like are familiar with linked list, it's like how you have when you're traversing, you have a node and which takes you to another node. But let's say when you're updating, let's just say none. Let's say when you're updating, and you want to take out, you want to take out, uh, this node. Let's take out node 2. You have to keep track of your previous node as well because when you take this out, well, you have to update the pointer from node 1 to point at node 3. So like sometimes when you're traversing a linked list, you might keep track of like previous node and your current node, and like say if current node dot item is equal to the item that you're looking for. Then you do uh, your previous node, um, what's it called? Next is equal to your current next. So that's kind of like taking this out. It's taking the pointer out like this. This might be a little bit too confusing, but if you're familiar with linked lists, think of it like you're keeping track of your previous and your current. So based off this, we can say uh, our S in in this formula, S is equal to self dot prev state, which we will be updating. A is equal to self dot prev action. R is just the reward that you get over here, which is passed in. And remember, our reward is given to us by an environment when you take an action, when you step in it. And then observation is your next state or S prime or current state. You can think of it however way you like. And A prime is the action that we just chose over here. So if we look back in the pseudocode, uh, and woo, we have Sarsa. Um, but if you look back in the pseudocode, the first thing for each loop is that we need to take an action. So that's what's happening here in our training loop. So for each episode, uh, this is what's happening in each episode. We compute an action. This is like our starting state. So think of this line as choose A from S using policy derived from Q. That's our start. And then this while loop over here is this loop where it starts saying loop for each step of episode. Um, take action A, observe R and S prime. That's what's happening here. So we take action and then we get a state and a reward. So this is S prime and R. And is terminal is used to determine if the episode has ended. If it has ended, we have a function called agent end. Oh, I don't think I have implemented this earlier. I'll go through this in just a little bit as well. So we have this uh there's something different that we have to do when an episode ends, so that's why this is something different. But um if the episode hasn't ended, then we have to choose another action. So over here, choose A prime. So that's our choose the next action from S prime. So that's uh, our new state. Choose an action from there. And then using this, we update our Q values over our Q function. Hopefully that's a little bit clear. Again, if you have any questions or any further questions, please message me. There's also a ton of resources online that you can look at, but without further ado, let's actually get into coding this Q update. So first things first, we need to access our Q value. So let's just grab that so we know what we're updating. Self dot, what was it called again? It was called action vals. Self.action vals, and we want the previous state and previous action. So if we recall over here, that's this. That's our pref state and self.prev action. So this is the thing that we're going to be updating. And what do we update it with? This TD error over here. So sorry if I scroll a little bit too much. So this is what we're going to be updating. And actually, all of these values are given to us because we pretty much have all the variables that we need to access it. So let's start off. Let's just call it TD error. Let's start off with this. And the first thing that was in the formula uh, is the reward. So let's grab that. And then we add it with a discount factor multiplied by Q S prime A prime. So here, A prime is our next action that we decide to take from S prime. And if you remember all of that, how we derived this, uh, we're going to be using observation and action, which we just chose over here. So we need to access our action values again. But this time, instead of previous state and previous action, we're going to use our current state and current action. The next thing that we need is we're going to subtract the original value. So let's do that. If you remember what it was, I'm just going to copy and paste it. It's just this. So now that I have a TD error, let's actually do the update. So it's going to be a plus equals alpha or step size multiplied by our TD error. So let's just type that in really quickly. Step size, step size multiplied by our TD error. Great. And if you guys remember, previous state and previous action is really important because like say if you're traversing a linked list and you want to do something, let's say remove a node, you have to keep track of the previous node. And that's exactly what's happening here. In order to do the updates properly, we need to keep track of the previous ones instead of looking ahead. So let's update our previous state to be the one that we're currently seeing right now, and our previous action. Yep. So hopefully this makes sense. Um, oh, and agent end. So something that happens when an episode terminates uh, is that there is actually no next state. Because when the episode is done, the agent is also done. So based off that, I'll give you a moment, like a little bit of time, just like a couple of seconds to think. What do you think should change about this TD error? I'll go back up over here as well so you can see a little bit. All right, if you need a little bit more time, just pause the video. Um, yeah, I'll just say it right now. The reason, we don't need this value anymore when we reach a terminal state. And the reason is, well, because there's no next state and next action to go to. When we're in a terminal state, the episode just ends. So we don't need to compute a new, we don't need to take another step in the environment to go to a new state because we're just completely done. So really, all of this, we can just copy and paste it. Let me adjust this a little bit and take out this value right here. There we go, over here. Yep, and this is our Sarsa agent. Did I run? No, no, I don't need that. All right, I'll leave this here for a little bit for you guys to see. So this is our agent step. We take an action. Oh, not JS. We take an action from S prime. Treat this as your A prime. And then using this S prime and our A prime, we update our Q function or our Q values of like reward plus what was it, gamma multiplied by our Q value from this S prime and A prime minus our Q value from our previous state S and our previous action A. And then we update our previous state and uh, previous action to be our current state and current action that we see. This is how epsilon greedy works. We don't really need to pay attention to this part. Actually, this slide. There we go. This is epsilon greedy. Whenever we're faced with the decision of making an action from a state, there's always the option of choose the best action that will give me the highest reward right now, or let's go explore. And that's what epsilon greedy is doing. So epsilon is a hyperparameter, which you can define, you can tune, you can play around with it to see what gives you the best outcome, what gives you the highest reward. Epsilon, think of it as your probability of exploring. Think of it as your probability of, oh, I want to come over here and find out. And the other 1 minus epsilon part of the time, all you're doing is like choosing the best thing that you know. So let's say if you're going to a restaurant and you always have this one dish, this one meal that you really like at this restaurant. So if you're being greedy, you're just always going to pick that because uh, it's what you like. It's what will give you the highest satisfaction based on your knowledge right now. But let's say epsilon percent of the time, you want to try something different or you want to explore other options. So think of epsilon greedy as just a way of choosing your actions. So if we come back over here, uh, this rand, it gives you a uniform sample, or it samples uniformly between 0, 0, and 1. So every space has a equal probability of being chosen. So let's say whatever this number gives, uh, the probability of this number being less than or equal to x is equal to x. So this is how we defined our epsilon, or like how we're defining our choose a random action or go explore. And this right here is just randomly sampling a new action. This one, yeah, all that it's doing is just randomly choosing an action from 0 until num action. So that's 0, 1, 2, 3. And over here is just exploiting. Um, I believe I explained it, but I'll just explain this again. Uh, Whenever you have like a list, there's a probability that all of these or there's a probability that there is more than one optimal. And if you have more than one optimal, let's say two Q values in one state, like you get 0.5 each. So one Q value is 0.5, another one is 0.5, and that is the optimal. What you want to do is that you want to make sure that you are choosing those with an equal probability. So if, let's say action one is gives you your optimal, action three gives you an optimal, you don't just always want to pick one over the other. You want to make sure that uh, you're sampling those uniformly as well. So that's kind of what's happening here. We first pick out the maximum value. And this one right here, np.where, this will give you uh, it will give you a nested NumPy array. And each of these elements inside is an index where your your what was it called again? Your Q value for the state is equal to your max value. So like in our example, this would give us in the example that I gave with like action one being the greatest and also action three, this would give us one and three as as a NumPy array. And that's why we have to index 0 here. Just so that because we don't want the nested list, all we want is this. That's why we have to index it. Don't ask me how that works. NumPy is magical. And then over here is just randomly sampling between those. Yeah, so this is pretty much epsilon greedy. This is your exploration. This is your exploitation. And this is how we choose our actions. Yes. And then if we run the training simulation, I'm just going to rerun some of these. Just give it a hot second. Almost there. Yeah, I guess while that's waiting, the most important thing that I didn't explain in person is that we need to think of your S prime, A prime as your current S and your current A. And uh, the previous S and A, you have to think of that as your previous S and previous A. Yeah, that's the most important thing. Um, yeah, and this is our plot that we get. So I believe this is the end of Sarsa, and we're gonna go back to what is it called again? We're gonna go back to the in-person lecture that we recorded.
So, okay, I hope you guys got the gist of SARSA. Let's move on to Q learning. Q learning is this. Okay, so let me explain. So it's basically
All of these are
SARSA.
TD.
Yeah. So you can see it only takes one step. But Q learning, do I have a SARSA thing here? No. But basically, SARSA, you randomly sample the next Q value, right? You have three actions in your next state, S prime, let's say, right? For SARSA, you randomly pick one of them. But for Q learning, you take the maximum action, in the sense that the action that has the maximum Q value. Yeah, that's basically the difference. Now, why is this important? Why is this? Why does this happen over SARSA? It's because Q learning directly learns the optimal Q function, so Q star. And this is why Q learning is the preferred method for most discrete, like tabular methods, so discrete state space, discrete action space methods. Because as soon as you get the optimal Q function, what can you do? Immediately get the optimal policy. Just remember that diagram, just go through and pick the largest Q value in each state. So this is why Q learning is the preferred method. And beyond this, later on in the policy, like in the more advanced reinforcement algorithms that use a Q function, they all build on this Q learning method. This method of reward plus the maximum over your next Q values. This is a very important algorithm. And in fact, what the professor will talk about next week is DQ, and it's basically an extension of this to continuous stage data with neural networks. And then later on, the state-of-art algorithm, they all use this, a manner of this algorithm, Q learning. So please, try that out.
When we were coding the thing we were just coding, didn't we also chose the maximum action, like the action that chooses the maximum Q?
Did we? I didn't do the coding exercise, did we? For Sarsa, you're supposed to. Well, we'll wait for Jessica to come back to answer that. But for Sarsa, you're supposed to randomly pick the next action. Did you guys do that? Sorry, I didn't do the notebook and I wasn't paying attention.
I think we have something random.
You randomly pick the next action. Yeah.
If we use the max, then if we get like multiple maxes, we randomly choose from the multiple maxes.
Oh, I see what you're saying. If they have, like if you have like tied or something, like the same.
Yeah. If you have like different, if you have like multiple max values, we chose like randomly. So
With,
no, we basically, I think for the
oh, Jessica, can you answer this question?
Yeah, sir.
Didn't I remember we like chose a list for a bunch of different actions that give us the maximum Q value in our code.
So I thought Sarsa's was.
Yeah, I was a little bit iffy on that one.
Did we do that, or was I?
This is,
not sure?
so I think what you're asking about the epsilon greedy, correct? Or,
Yeah,
Like-
max indices.
yep,
Oh.
what we're doing here, oh wait, hold on a second.
Oh, I see.
This might be wrong, wait.
What's what?
No, here we're doing epsilon. Did I do the wrong one?
Wait, why is it wrong? You pick
Should this be random or?
action? No, I mean the action. It's a policy. You just pick it's this epsilon greedy policy, but the Q value selection, you select the random Q value.
Q value selection, you select the random Q value.
Right? Yeah. Yeah. You randomly sample the next action, and then you.
Oh, yeah.
It
Wait.
should be. So, you want to explain the max?
Let me double check something one second.
Basically, the max there is in a state. Epsilon greedy is in this particular state with probability epsilon. You pick a random action to choose, but with the probability 1 minus epsilon, you pick the action with the greatest Q value in the current state. For Q learning, the next state, the target, the TD target. You use.
I think I was looking at the wrong solution.
Wait, what? But why is this incorrect?
Oh wait, hold on.
Well, I don't see why it's incorrect. In the current state, you use epsilon greedy epsilon selection. Meaning, in the current state, you pick an action
Oh no, this is
that
correct,
corresponds with the highest Q value, with some probably 1 minus epsilon. With probably epsilon, pick a random action. It's to balance exploitation. But when you're doing the next action, right? Hang on.
There's a reasoning for this. My brain's not working right now. I apologize.
Yeah. Yes. So it's correct. It's just that you're not picking the maximum action because with the probability of epsilon, you pick a random action. You see? It's just that most of the time you pick the action that has the highest Q value. But with a probability of epsilon, you use a random. So the policy we're using is epsilon greedy, so it's a little bit contrived because epsilon greedy most of the time picks the highest Q value.
But it doesn't guarantee.
It doesn't guarantee it's all. So if this, let's say, for example, this were a random policy, you pick a random action at random without considering the Q values. For SARSA, you just randomly pick. With 25, let's say there are 4 actions, you pick 25% chance each. With Q-learning, there's a 100% chance you pick the one with the highest Q value. Do you see? It's just that the policy we happen to be using it is epsilon greedy, which usually picks the highest Q value. That's why there's a max, right? But sometimes with probability epsilon, we'll pick a random action.
I guess like if you want to go full on random, you literally just use random here.
Yeah, you use
So
random.
it doesn't like smaller than epsilon. You just
Yeah.
It's kind of like that. You don't do the smaller epsilon. For
go full
Yeah.
random.
for
and then-
for the next state, when you're calculating the value of the next Q value. For the current, when you take a step, you still use the same policy, whatever it is. But for the next Q value, you look at all the actions, all their Q values, and you pick the largest one. It's independent of policy. It doesn't matter what policy you use for Q learning. For the next for the next Q value, you just pick the maximum one. Do you see?
for the next Q value.
For the next Q value, because you can see here, this is Q of S of t plus 1 and A prime, meaning the next state and next action.
But it doesn't care about which action. It's
Yeah,
like
yeah. You just pick the one with the highest Q value. Yeah.
So the difference between Q-learning and what we're doing before was the next action was either we use like epsilon greedy or full on random. Here,
Yeah.
it's always the max.
It's always the max. You get it? Yeah. But when you're transitioning, like when you're taking a step, like to get this reward for SARSA and Q learning, you need to take a step in the environment, right? In order to get the reward. Yeah.
so is the Q value like within the action or is it within the state? So because how could we know if it doesn't depend on the next
policy.
state, right?
No, it does depend on the next state. It doesn't matter what policy you have, because you remember, you have a table, you have a repository of all the state and action pairs, right? Let's say you in this case, you're in state 2, starting. It's a uniform random policy, right? It's a uniform, for every single situation, it's a uniform random policy. You take a step, right? And then I could have picked left or right here. I just happened to pick right with 50% probability. If this was Q learning, let me just go on with the lecture. Maybe you can understand. Hang on. If we go on with Q learning, I'm just gonna ignore this, just because it's not important. But yeah. With Q learning, you start with 2, right? The same thing. Once again, it's a uniform random policy. Reward is 0. Now you're in the next state, right? This action was selected uniformly at random, right? Because that's the policy. You selected action at random. And previously in SARSA, in here, you also selected action at random. It just happened that I chose right and right. Now in this case, Q learning, you have these 2 state action pairs. You pick them, you know all the Q values of every single state action pair. That's how Q learning and like PD and tabulous, like multi-call, everything works. You know the Q values. You pick the one with the highest Q value. So here, notice, it doesn't depend on the policy. I didn't say, I randomly choose one of these. I always pick the one with the highest Q value. And then you do the update. You see that? So in the thing you just did with SARSA, the policy itself was not a uniform random policy. It was an epsilon greedy policy. Meaning that with probability epsilon, you pick a random action. With probability 1 minus epsilon, you pick the one with the largest Q value. It just so happened that epsilon greedy policies, epsilon is small value. So usually you pick the highest Q value, usually, right? But at this, if it's Q learning at this next stage, you ignore the epsilon part, you ignore what policy it is. You look through, you arrive at your next state, 3, you look through all your next actions, whether it's left, right, up, down, for whatever it is, and you pick the one with the highest value. In SARSA, you don't look at all the actions, all the states. You sort of query your policy again and pick an action. In here, you do get it now? Do you understand?
So right now, Q learning is when we know the next state is state 3. And then we check all the possible state actions that is in state 3.
Yes,
And
yes.
then we see that the state action with 3 right,
Yes.
gives you Q plus 2.
Is the
But
highest.
if you do, when you're at state 3 and then you do left, you're gonna go back to 1. So that is not as desirable. Right?
Yeah,
Also-
you just
That's not as good.
you pick the highest value.
Yeah, I'll say, here we got a little bit lazy just using the action just using the next action that we're gonna be doing. But let's say if we wanted to do a little bit more technical, we do, or let's just call it SARSA. Let's call it SARSA action. Rand generator choice. What do we do over here? Yep, random self-done. If you wanted to get a little bit more technical,
Well, okay, that's close.
do you see what I'm doing?
Yeah, but the policy isn't always randomly, so I'm trying to convey the fact that
Oh yeah.
like you pick an action according to a policy. It's not like you randomly pick an action.
Oh yeah, true.
You pick an action according. How this?
Okay.
We need to continue with the lecture.
Yeah.
We can clear this up like afterwards individually. Like you pick an action according to the policy. Does everyone else? If you guys have any questions, just come to me later. But I hope you guys understand. Like SARSA, the next day you look at your policy and pick an action according to it. For Q learning, you don't look at a policy. You just pick the maximum Q value. Wait, is that? Oh, okay. I'm out again. That was quick.
Oh, okay.
So yeah, now you do Q learning. Hopefully you can see a difference. Hopefully this will clear up. And yeah, we'll have.
Okay. Yeah, no, we'll finish. Yeah, so I guess with the confusion that between SARSA and Q learning, I guess you guys can see how closely related these different algorithms are. So like, again, the only main difference is this max right here. Yeah, and then if we look at our, here when we're choosing, it's back at SARSA, when we're choosing an action, our next action, we're just using the policy that we used, or like the policy of the agent. But in Q learning, where did that slide go? In Q learning, do you see how we're missing choose next action based on what's it called? Based on your policy. Do you see how we're missing that line? So if we go back to SARSA, SARSA is missing this line right here. Choose next action using policy derived from Q, usually epsilon greedy. That's the clear difference. And so instead, to replace the choose your next action, we just choose the argmax. We choose the action that will give us the best. We use the argmax action to update our policy instead of just using our policy. Or sorry, let me rephrase that. We're using the max. We're using the action that will give us the max Q value to update our current state action pair compared to just a random action that we sample using our policy. One is using a policy, the other one is just is using the maximum value. Yes? So if we scroll down to in the notebook to our Q learning agent, a lot of this is going to be really similar. So the reason why we still have an action, we sample an action using our epsilon greedy is, well, we have to choose an action to act in our environment, and we do that using our epsilon greedy. What differs here is how we are updating our Q function. So Again, we're going to be updating self.action values. So this is going to be our Q function. And we are still going to be updating our previous state and our previous action. But what goes here is the difference. So let's call it TD error again. And we still have a reward. And but this is the main difference. So what we need to do is that when we are looking at our next state, so that's going to be our observation. When we're looking at our next state, we just need to pick the maximum value of these state action values for this state. So really all we need, we just take the max. And remember, like, what this does, before what we were doing is that we were picking a specific, sorry people online if you can't see the blackboard, we were picking a specific state action to do the update. But now, let's say in our, let's say if we're looking at the second line, if we're in this state, if we were in SARSA, epsilon greedy might have given us, if these are our actions 0, 1, 2, 3, epsilon greedy might have given us this 0 point action 1, which has a state action value of 0.2. SARSA might have given us that, and we would use that to update. But in Q learning, we don't really care about what our next action is. We just pick the max. So in this case, we would just pick the 0.4. Yep.
Right, so here we are more focused on exploitation instead of exploration.
This isn't really interacting with. Currently, you're not really interacting with your environment. You are more so choosing the best option to update our parameter or our state action value with. Yeah. So with epsilon, this is kind of like, imagine if you're being optimistic about the state that you're in. And you're choosing to update it with the maximum possible or like expected value, yeah.
Why is this better?
Why is this better? Do you want to take a guess? No, it's okay. So the reason why this is better is because, let's say,
It learns the optimal.
Yeah. It learns the optimal like a lot, just a little bit faster. And also, like, if you're in this state and you randomly sample a 0.2, well, that's not really the best that you can do. The best that you can do is picking a 0.4.
Yeah, so Q learning, SARSA does not learn the optimal Q value. It learns the Q values for this particular policy. It's like policy evaluation. You evaluate the current policy and get the Q values. And then what you do afterwards to get a better policy is you act greedily. It's like, remember the policy iteration framework? That's what SARSA is. You evaluate the current policy, get the Q value, greedify, and then repeat. Q learning directly just learns the optimal Q function. So once you're done with Q learning, you greedify once, and that's the optimal policy. The reason it learns the optimal Q value is because of the max operation in there. It's derived from the Bellman optimality equation. Yeah, go ahead.
It's key learning is that what's the point of using source
Very. Wait, do you have the thing with the safety?
Yeah, but it's coming up.
It's coming up.
It's coming up. Yeah.
Very good question, though.
So So essentially, like, yeah, the only main difference here is just this max right here. It's picking the optimal. It's picking the best one. And we do the same update. So that's our TD error. So that's the stuff inside the brackets. And now we multiply by our step size. And then we also update our previous state and previous action. Oh, whoopsies. Yep. And then if we run this, let's do its training. I can see a little bit of confused faces. Feel free to ask more questions if need. Yeah. And also, don't be alarmed if it is a little bit confusing. I think I took maybe a week to understand all this, so like
See, like
a lot of review.
how deep learning and neural networks doesn't help with anything.
Yeah.
But anyways, yeah. Any questions, please?
But like the main idea of these like TD is like you're actively updating as you're stepping through the environment.
Also, the reason were coding these is because, as I told you before, that you want to learn the Q function, not the V function. Once you get the Q function, you actually improve the policy. Yeah, go ahead.
Wait, sorry, so why don't we just always exclude learning?
Well, that's coming up, right? You have to.
Yeah, Q learning versus
I
SARSA.
can tell.
Yeah. Do you want to go through the slides first, or do you want to? Oh yeah. This is all there is to this.
Very simple.
function, yeah.
Well.
What's next?
It's expected SARSA.
Oh, expected SARSA? Okay, let's not do that. What we want to do first actually is let's compare the two. So let's just plot these first. We can kind of see how SARSA, it does a little bit better than Q-learning. So essentially what's happening in like this little blurb, so SARSA is something called an on-policy algorithm. So it's basically updating the value, state action value functions based on the current policy. It's using the policy that it has to actively update our Q function. Yeah, so as like here it says, so one of the main things is like if the agent sees a bad state, so like if it falls off a cliff, this will impact the update a lot. And again, it's updating based on its own policy, and therefore it will be less likely to visit this bad state again. But if we look at Q-learning, it's something called an off-policy algorithm, which it's not really, it doesn't really learn the policy that it's currently following. So it might be using an epsilon greedy policy, but if you remember, when we're updating it, we're not using the epsilon greedy to actually update it. So like just reading this little, continuing on, this can be seen with the max operation in the update equation. The update is done as if the agent is following the optimal policy. It's not following the policy that it's using, if that makes sense.
Okay, well, I don't think optimal policy is like what these.
Okay, probably not. But.
So I don't think. But so in Q-learning, why not always use Q-learning? So Q-learning learns the optimal value function and then adopts this Q function, and it. Do you have this thing of it like falling?
The video? Yeah, I have a video. Or the falling off?
Yeah, do you have it?
Or I have videos. So this is SARSA. Or an example of SARSA.
Okay.
And then let's look at Q-learning.
Do you notice what is the difference between these policies? One walk up there, one walk down here. Let me ask you this: if you were here, go ahead.
Sorry, I think Q learning doesn't whereas the other one is more open to exploration because it's taking random directions.
It's kind of a great idea, but first of all, look, do you notice Julian walks up here, so walks up. So let's say as a human, you're walking on a cliff. Where do you want to walk? Where do you want to walk? Like if you walk on this cliff, would you walk here? No, you want to walk up there, right? But notice this is a lower reward because what's the reward? -1 per time step. Right?
It's -1 per time step.
So you can see it actually takes longer to walk up there. Sarsa does worse, object reward-wise. Okay, reward-wise. Tuning does the best. This is the optimal policy. You just go along here, right? You just walk along here. But is this like, let's say you're driving a car, you're teaching an autonomous car to drive a cliff along here. Do you want it to drive like this? No, right? You want some safety.
If it doesn't turn left, there's no problem.
Yeah, exactly. Right?
But then you can't get to the end, and so like you just get negative. You just get
always
infinite.
knows the best.
Negative infinite.
But is the best always the best? You know what I mean? Like, sure, numerically, -1 reward around here, right? Because this takes the shortest path. But, maybe Sarsa is better. You prefer this. Does that make sense?
But then how does the graph above, like when you graph the two Sarsa and Shu, how do you graph so one blue and one orange?
Which
how
one
was
would
that thing?
This one?
No, not this one. What about it?
Oh, did I? Are these
It's
labeled?
the same, right? No, because Q learning takes the optimal route, the route closest. No rewards. I mean, no wasted motion. Because the reward is -1 per time step. The faster you finish, the better you do, right? Rewards wise. So Q learning finishes fast by walking along the cliff edge. But Sarsa does worse because it like sort of, loops up, like it like.
Oh, I think what he's confused about is like when we said like Q learning it does better than, but like why is Q learning of course as in here?
Oh.
Yeah, isn't Q learning supposed to be the best?
Not necessarily.
Because does it fall? What are
The reason why Q learning is like here we're doing a lot of samples or like we're running a lot of episodes. We previously ran a lot of episodes and this is just plotting the mean of those. If you remember from Q learning, it was walking really close to the edge. So it could have just fallen off the edge really easily and that would have given a -100 reward for that episode.
Because our policy at the end is still stochastic.
Our policy at the end is still.
Actually, wait.
It's epsilon greedy
Do you update the
still.
policy at all? Do you update the policy?
No, it's just epsilon greedy.
It's always epsilon greedy?
It's always epsilon greedy.
Wait, what is this graphs? Sum of rewards during the episode.
Wait. Did I do this one?
Wait, if you're not updating the policy. Oh, no, that makes sense.
No, that
That makes sense. Yeah, because it's so stochastic. Towards the end, the policy is still random. It's so epsilon greedy. So sometimes currently walks off the cliff. It gets -100 reward.
So imagine basically, I'm walking along a cliff. There's a possibility that I just randomly walk off the cliff.
Because but in our case, we're using a stochastic policy. Random policy. Epsilon greedy has randomness. Yeah.
What about if we train using Q learning first over the function and then we switch to deterministic
Then it will never fall off the cliff. Then it will always be better. But in our case, we never made it. Towards the end, what you do with Q learning is you act greedily with respect to the policy, and you gotta determine a non-random policy that always takes the same route, and you will never walk off the cliff. But in our case, we're using an epsilon greedy policy, so sometimes it still walks off the cliff. You see, that's what we're trying to illustrate with this environment.
Oh, so
Yeah.
the epsilon greedy, the policy still impacts Q learning a bit.
Yep.
Yeah, because we never fixed the policy. Do you see what I mean? We never changed it. It's still epsilon greedy. Do you see what I mean? Yeah, go ahead.
But I thought Q learning was just a high speed color, so why would it?
That's in the updates.
Yes.
Here, when we're choosing when we're updating it, do you see Q learning? Because this is the fastest route, the Q value when it's doing the updates, it's just going to use these values here.
Okay.
Yeah.
But then, because of this, when we're doing epsilon greedy, it's going to most likely choose it's most likely going to be choosing these actions over here.
Right, okay.
But then, when you're in these states, you just have a possibility of falling off the cliff.
Yeah.
So that's kind of why if you do this over a bunch of different episodes, that's why the mean reward for like that,
Yeah, for
that
Q-learning
episode
is
going to be
is
a
lower.
Yeah.
Is lower. That's why. So there's a reason we chose this environment, cliff walk. It's precisely because to illustrate, yes, Q-learning achieves a lower, like if the policy was deterministic, if
It's perfect.
it's
Yeah.
perfect, that this is the lowest, highest reward path you can take, right? Everyone agrees. If the policy was not random, that is the worst path. But the policy is random. We kept it random because, you know, in the real world, let's say you train a car to drive around the cliff. Even in simulation, let's say it's perfect. In the real world, something might happen. Maybe there's extra strong wind that day. The car might fall off the cliff. So we normally with Q-learning, normally when you're done with the R algorithm, you don't want to have a random policy. You want to fix a policy, right? Because you don't want, if you already have an optimal policy, you don't want any more exploration, right? Because it's already the best. But in our case, we kept it random to showcase the fact that you don't always want to do Q-learning because it like jumps off. It's not always the best case scenario. Do you see what I mean? If we wanted to just solve cliff walking, right now we turn off epsilon, make epsilon 0, and make it always go along the graph. Right? Does that make sense? So this is why you would use because Q-learning and oh my gosh, it's just really not enough time to explain it, but the max operation is not always desirable because it's not the experience of the agent. Let's say, right? You have a stochastic environment, meaning the transition dynamics change. That's not usually the case. Let's say you're walking along a street, and today it's really windy, right? Oh no, today's not windy at all, right? You use Q-learning, you always pick the best, the next Q value, you get the optimal policy. And then SARSA, you sample from your own policy. Let's say your policy is to always do something. You react to the environment, right? Because that's the policy. You do it, right? Today is not windy. You get that. But tomorrow it's extremely windy. It's extremely windy, and so the environment has changed completely. Q-learning will still like sort of treat it as if it's like no difference than the previous. It will take the max actions. But if you're using SARSA, your policy, like you'll know that it's windy and you'll take different actions according to the stage you see. Do you see what I mean? Do you kind of get that? Max is not always the best. Sometimes you want to learn according to your experience rather than just whatever is the best. Do you see what I mean? That's why sometimes it's safer. SARSA is safer. And there's a big issue so Q-learning is the lowest level. DQNs are
Next week.
It's pretty, is it bad? It's not the best because of this issue. They use Q-learning to update their neural networks. What ends up happening is the max operation sort of makes, I don't want to go into detail, but it sort of messes up the policy because it overestimates the Q value because the max, you're taking the max. So for certain actions that are unseen, you take it overestimates the Q value and it leads to catastrophic performance. Lots of later algorithms, pretty much all of them, DDPG, whatever, they try to solve this issue. So max is good because you learn the optimal, but it's not always good because you want to sometimes learn according to your own experience. But here's the reason though, that Q-learning is almost always preferred, is because most of the time, it's inefficient to learn from your own experience. Let's say we're trying to go to the moon, right? Do you think it's feasible to every time to send a robot up to the moon, have it bump around, crash, and waste $1 billion each time? No, right? To learn from your experience. What is better is you send a person up to maybe the next mission with SpaceX or something, have a human walk around, collect their experience, and have the robot learn from their experience. Do you see what I mean? Do you see what I mean? So sometimes it's not always feasible to learn according to your own experience. Sometimes you have to learn based on another person's experience. This is the difference between on policy, your experience, and off policy. That's what Jessica was trying to say. But it's okay if you don't get that. But just understand that sometimes the max operation is not always the best. That's basically it. In this case, due to safety, or whatever, or if the environment changes. Any questions? Yeah, go ahead.
I just want to confirm, so with SARSA being on policy, it's kind of like you have this agent following us in like its current policy, and every single time it takes a step, that's when it updates its policy again based on its feedback.
Yeah.
And then for Q learning, it's basically going through everything, following a single policy, then looking back, thinking back, and determining how it can improve. Does that
No, they both do that. They both take an action, take a step, look back, get some feedback, which is the reward, and see how they improve. The difference is the way they do the improvement. SARSA uses its own policy at the next state to improve. It takes, so let's say I'm here. This is one state, that's next. SARSA says, okay, I'm gonna follow my own brain. My policy, take a step. I come here, I get some experience. Now I'm gonna randomly pick an action using my own brain again, and use that to improve, using my own experience to improve. Q-learning at this stage uses its brain. I'm using my own brain, go here. Here I turn my brain off. I just say, okay, whichever is the best option here, I just go for it.
So
Right.
I think that's what I was.
Okay, sorry if I misunderstood.
Where like Q learning is more like experience replay, runs through it, then improves based on that.
Yeah, sure.
Improves based on that. As far as like improves its brain at every single.
You can, sure. Yeah, it's kind of like that. Off policy and on policy is basically the difference, but it's a little bit hard to wrap around concepts. But okay, any questions, please ask. I will stay behind. We're out of time, but I highly recommend you go through the rest. This is expected SARSA.
I'll just say expected SARSA. It's pretty much the same thing as SARSA, but really, instead of randomly sampling an action or using your policy to sample an action, you just take the expected value.
Yeah,
That's literally.
but I've literally never seen this.
Really?
Really? When have you seen it?
Oh yeah, fair enough. I always use
But it's a more stable version of SARSA. It's actually better than
it's better than SARSA.
it's better than SARSA.
Is it?
Yeah, it's better. Yeah, but it's slower but better than SARSA. But yeah, we won't go through this. But basically, just this slide. You start. This is your next day action pairs. Q learning, you would pick Q equals 2. SARSA, you pick on randomly. Expected SARSA, you weight each Q value down there by its chance of happening.
Weighted average.
Weighted average. So it's a uniform random policy, 0.0, and then whatever. And this is a main lecture series. Thank you, Alex, for coming. What's next? There's another one next week with DQNs and Jessica and Professor Bowling. So please come to that. It's very amazing. And there's an RL tournament next semester, and it's an amazing chance to learn and play RL. Okay, and this is sort of me trying to influence
I'll go
your
over this
future.
next week. I'll go through that next week.
Yeah, but let me just say quickly. There are two ways to consider a reinforcement learning problem solved. You can either have the optimal policy or the optimal Q function, not the optimal V function, the optimal Q function. Some methods, you just ignore the text here. Some methods directly learn the policy. They don't have a Q function. They don't learn the Q function at all. We have not talked about that at all in this course. They're called policy gradient methods. The other methods, like SARSA, Q learning, whatever, they learn the optimal Q function, and using that, they do the act immediately thing, right? You guys. So it's basically the same thing, but I'm just saying there's two sort of classes. You can either focus on learning the policy itself, ignore Q function, or you can learn the optimal Q function and then use that to get the policy. And then I think probably next week is better, but these are the things. These three are the ones. I think if you guys want to continue with reinforcement learning, these three are the ones you'll see pretty much everywhere. That was used to train ChatGPT. These two are everywhere, and these really build on these. Ignore that for a sec because we didn't talk about them. But these deep Q networks is basically Q learning. If you know Q learning, you're on your way to understanding what these are. I think it's really exciting because these are very practical algorithms. Just for future directions, you guys want to go and explore more. If you guys are curious about any of this, I can explain it. You're gonna get a head start. I can explain it after the lecture today. But that's basically it. That's the mini lecture series. There's still, is this the right QR code? Probably not. Oh, it is?
I think so.
Okay. But if you can, this is the end of week 3. Please feel free to approach us, ask questions. We'd be more than happy to explain. And RL, just to summarize, it's a very exciting field. It's very different than what you've learned so far, but it's very powerful. And I think, as I said in the first week, it's the most similar to how humans think, in my opinion, learning from feedback. Technically all of RL is learning from feedback. I mean, all of machine learning is learning from feedback. But anyway. decision-making stuff. But yeah, so thanks guys for coming. Feel free to leave. But yes, but once again, next session, next week. And if you really just want to take away 2 things from this lecture, just 2. Why you would learn the Q function over the V function, why? And the algorithm of Q learning. Because every single other algorithm we've talked about in this course, in my opinion, pales in comparison to Q learning's importance and prevalence. So yeah, please just learn Q learning and why the concepts of V and Q I think are very important. What they are. Yeah? Thanks, guys.
Honestly, thank you for coming.
Yes, thanks for coming. Truly, thank you. And yeah, if you're interested in anything else, like any questions, any of these algorithms, you can ask me about it. I think I can explain them. And then, yeah, just anything.
I'll leave this here actually.
Or like what we talked about, why you would prefer TD over Monte Carlo.